Assalamualaikum and salam sejahtera. Today, I would like to discuss on chapter 27. The title here is the quantum physics. So, unit of chapter 27. So, the first one here is the 27.1 is the black body radiation and the Planck's hypothesis. Then we go into 27.2, the photoelectric effect and the particle theory of light. And then we go into 27.5, the Compton effect. And the last one here is 27.6, the dual nature of light and the matter. Okay, so we go into the 27.1 is a black body radiation and the Planck hypothesis. So at the end of the lesson, the student should be able, the first one here, to define what is a black body radiation and then explain the Wien's displacement law, the Planck quantum hypothesis, and also the quantized energy. So, an object at any temperature emits electromagnetic radiation. So, in this case, this one we call it as a thermal radiation. So, Stephen described the total power radiated. Okay, so the spectrum of the radiation depends on the temperature. And the second one here is the properties of the object. Okay, at low temperature, the wavelength of the thermal radiation are mainly in the infrared region, okay, and hence not observable by the eye. But at the high temperature, object eventually begins to glow red. So the spectrum shows a continuous distribution of the wavelength from the infrared, and then we go into the visible and also the ultraviolet. Okay, so when you compare to this one, infrared, visible, and ultraviolet. So infrared here should be the longer wavelength, okay, compared to the ultraviolet. Okay, when you look at this one, okay, due to Stephen's law, at the low temperature, so basically here the wavelength at the infrared region. So means that here at the low temperature, so the wavelength may be at the, so this one is a longer wavelength. Okay, so at the high temperature, the object eventually begins to glow red. So glow red here, basically this one is due to a visible light, right? So means that here this one should be the shorter wavelength compared to the infrared. Okay, so this one is due to the visible part. Okay. Okay, the classical view. Thermal radiation originates from accelerated charged particles, so near the surface of an object. Okay? So problem in explaining the observed energy distribution as the function of the wavelength in the radiation emitted by a black body. So what is a black body? So basically, black body is the ideal system that absorbs all radiation incident on it. Okay, so an opening in a cavity is a good approximation of the black body. So the nature of the radiation emitted through the opening depends only the temperature of the cavity walls. Okay, so here you have a diagram of the black body. So here you have a small opening here, and this one here you have the incident of light. Okay. Okay, so as light enters the cavity through the small opening, okay, so part is reflected and part is absorbed on each reflection from the interior walls. So means that here, this one you have the light here, okay, coming to the small opening, okay, and then going to this object, and then part of the light should be reflect, and part of the light should be absorbed in this wall, same, and part of the light reflect, and finally all the light should be absorbed in this interior wall. Okay, so after many reflections, essentially all the incident energy is absorbed. Okay, so objects that are highly effective and shiny are poor representations of the black body. Means that here, if you have the material here is shiny or highly effective. For example, here I think it's a mirror. Okay, when you put here a mirror inside this one, okay, this one is a poor representation of the black body. So this one is the graph of intensity versus the wavelength. Okay. So the experimental data for distribution of the energy in black body radiation. Okay, so the radiated energy varies with the wavelength and the temperature. Okay, so as the temperature increases, so the total amount of energy area under the curve should be increases. So as the temperature increases, the peak of the distribution shifts to the shorter wavelength. When you look at this graph of intensity versus the wavelength, so for the red color here, okay, so what happened to this one? So this one is the maximum temperature. Okay, so compared to this one is a smaller temperature. Okay, so when you look at this amount of energy, so amount of energy is based on the area under the curve here. And you look area under the curve due to the higher temperature. When you compare to the temperature, the lower temperature, so the area here should be smaller compared to the higher temperature. So indicate that here. So when your energy, not energy here, when your temperature should be higher. So what happened to your energy due to area under the curve here should be higher also. Okay. And then number two, when you look at this one, okay, this one, when your temperature here is a 400 Kelvin. Okay, so what happened here? Your graph here, I mean your peak here should be shift to the shorter wavelength compared to this one. This one is shift to the longer wavelength. Okay, so you can conclude that if your temperature should be if your temperature is smaller, so what happened to your peak here, peak of this graph should be shift to the longer wavelength compared to this one. So this one you have the higher temperature. So what happened to this graph should be shift to the shorter wavelength. Okay. So means that here you can conclude that so the higher the temperature, so the higher the energy, then the higher the temperature, indicate that your peak of your graph should be shift to the shorter wavelength. Okay. So the wavelength of the peak of the black body distribution was found to follow Wien's displacement law. So lambda max T is equal to 0.2898 times 10 to the power of -2. So this one is a meter Kelvin. Okay, so lambda max here, this one is the wavelength at which the curve peaks. And then T here is the absolute temperature of the object emitting the radiation. So comparison of the experimental data with the classical theory of the black body radiation. So this one is due the ultraviolet catastrophe. Okay, so classical theory did not match the experimental data at long wavelengths. So the match is good at a short wavelengths. So the classical theory predicted infinite energy. Okay, so at a short wavelengths, so experimental showed no energy. So when you look at this graph, okay, so same here you have a graph of intensity versus the wavelength. So you have a blue here. The blue here indicate for the experimental data, and the red here is due to the classical theory. Okay. Basically, the experimental data coming from this graph. Okay. So, and this one is due to the classical theory. When you look at this one, okay, so at the longer wavelength here, so what happened between the classical theory and the experimental theory? So basically at this position, so this one is the wavelength is basically is matched. Okay, so means that here this one is no effect. Okay, but when you look at the shorter wavelength here, let's say at this position, so what happened to your experimental data and the classical theory? So at this position, when your wavelength should be shorter here, so your classical theory did not match. The graph here did not match with the experimental data. Okay, so when you look at at the short wavelength here, okay, at the short wavelength. So what happened to your your experiment here? So your energy here indicate that at this position your energy become 0. Okay, but for a classical theory, this one is going to the infinity. So indicate that at a short wavelength, the classical predicted infinite energy. So Planck hypothesis that the blackbody radiation was produced by resonators. So resonators were submicroscopic charge oscillators. So the resonators could only have discrete energies. So En is equal to NHL. So basically before this, we already discussed on the formula of energy. E is equal to HF. But this one is due to the Planck hypothesis. So N here, okay, indicate that this one is a positive integer called the quantum number. So the value start with the number 1, 2, 3, and going to infinity. So F here is the frequency of the vibration, and the H here is a Planck constant. So the value is 6.626 times 10 to the power of negative 34 joule second. So in your calculation, so basically, so we are using the value is 6.63 times 10 to the power of negative 34 joule second. Okay, so the key point in the Planck theory is the assumption of the quantized energy state. So Planck's assumption of quantized energy state was a radical departure from classical physics, is the quantum leaps. So the quantum leap, and that led to the totally new understanding of the nature. So the fact that energy can assume only certain discrete value, so is the single most important difference between quantum and the classical theories. Okay. So classically, so the energy can be in any one of the continuum of values. Okay, so we continue on 27.2. So the photoelectric effect and the particle theory of light. So at the end of the lesson, the student should be able to define photons and its properties. And then number 2, describe the photoelectric effect. Number 3, discuss the non-classical features of the photoelectric effect and their explanations using photon theory of light. And the last one, apply the photoelectric effect equation to quantum systems. Okay, so when light is incident on a certain metallic surfaces, electrons are emitted from the surface. So this situation, we call it as a photoelectric effect. Okay? And the emitted electrons, we call it as a photoelectrons. So the effect was first discovered by Hertz. Okay, so the successful explanation of the effect was given by Einstein in 1905. So in this part, so Einstein received the Nobel Prize in 1921 for paper on electromagnetic radiation. of which the photoelectric effect was applied. Okay, so this one is a photoelectric effect schematic. Okay, so here you have a diagram. What is this one? So this one is a diagram of the photoelectric effect apparatus, and this one is the evacuated glass tube. Okay, so evacuated glass tube basically known as a photocell. Okay, so here you have a E here. E here is the emitter. So the emitter here is connected. Okay, connected with a negative variable of power supply. And then this one is a C. So C here is the collector. Collector here connected with the positive variable power supply. Okay. And look at this one. When the light strikes E, okay, when the light strikes E, so what happened? Photoelectron are emitted. Okay, photoelectron here emitted. Okay, what is a photoelectron? So photoelectron, so going back to this one, is the emitted. So the emitted electron. Okay, and then electron collected at C. Now electron collected at C here. Okay, and passing through the emitter. So here you have emitter, and this one you have a voltmeter. Okay, so again, electron collected at C and passing through the emitter. Okay, create a current in the circuit. So C is maintained at the positive power supply. Okay, so basically, when the tube come in the dark place, for example, so what happened at that situation? So your emitter should be 0 value. But if you have a light here, enter to this emitter, for example, the wavelength of this light, okay, the wavelength of this light is shorter compared to the wavelength of the emitter. I mean, the wavelength due to the material in this emitter lah. Okay, so what happened? Suddenly, the emitter read a current. Okay. So here is the graph of the photoelectric current versus the potential difference between E and E, between the emitter and collector. Okay. So at large value of delta V, the current reached a maximum value. Okay. So the current increases as the incident light intensity increases also. Okay. So no current flows for voltages less than or equal to negative delta Vs. Okay, so the stopping potential. So here, delta V here is a potential difference. Okay, and delta Vs here is a stopping potential. So here, when you look at the graph of current versus the applied voltage, okay. So at the large here, value of delta V at this point. So what happened here? The current, okay, from this low intensity graph, a blue graph here, reach a maximum value. Also for the high intensity here, the larger voltage, so the current reach the maximum value. Okay. And then the current increases as the incident light intensity also increases. Okay, so means that here, when you compare with the high intensity and the low intensity, at high intensity, so what happened to the current? Current also high, but at low intensity, the current should be lower. Okay, so we conclude that here at high intensity, what happened to the current? Current also higher, but at low intensity, the current should be lower. Okay, so when you look at this position at stopping potential here, so what happened to your current here? At stopping potential, for a graph of high intensity and low intensity, both here become 0. Okay, so indicate that here at this situation, at stopping potential, what happened to your current? So your current here become 0 current. So the stopping potential is independent of the radiation intensity. Doesn't matter whether your intensity is higher or low intensity. Okay, but at that, at stopping potential, what happened to your current? Automatically it becomes 0. Okay, and then the maximum kinetic energy of the photoelectrons is related to the stopping potential. So here Ke max is equal to E delta Vs. So E here is the electron, delta Vs here is a stopping potential, and Ke max here is a maximum kinetic energy. Okay. So this one is several features of the photoelectric effect can't be explained with the classical physics or with the wave theory of light. Okay. So number one, no electrons are emitted if the incident light frequency is below some cutoff frequency that is characteristic of the material being illuminated. Okay. So the wave theory predicts that the photoelectric effect should occur at any frequency provided the light intensity is sufficiently high. Okay, so next one, number 2. The maximum kinetic energy of the photoelectrons is independent of the light intensity. Okay, but due to the wave theory, a light of higher intensity should carry more energy into the metal per unit time. Okay. Next one, number 3. So the maximum kinetic energy of the photoelectron increases with the increasing light frequency. Okay. So it means that here Ke max is depend on the frequency. But due to the wavelength, the wave theory, not a wavelength, due to the wave theory, so there predicts no relationship between the photoelectron energy and the incident light frequency. Okay. Next one here. Electrons are emitted from the surface almost instantaneously, even at the low intensity. Okay. Due to classically, we expect the photoelectron to require some time of absorb the incident radiation. Okay. Okay, so this one is the Einstein explanation. A tiny packet of light energy called a photon. Okay. So this one is not proton, this one is a photon. What is a photon here? Is a tiny packet of light energy. So would be emitted when the quantized oscillator jump from one energy level to the next lower one. Okay. Extended Planck's idea of quantization to electromagnetic radiation. So the photon energy will be formula E is equal to h(L), where E here is the energy of photon, h(L) is a Planck constant, so the value is 6.626 times 10 to the power of negative 24 joule second. So basically, in your calculation, so here you are using 6.63 times 10 to the power of negative 34 joule second, where F here is a frequency. So each photon can give all its energy to an electron in the metal. Okay. So the maximum kinetic energy of the liberated photoelectron is Ke max is equal to HF minus V, where HF here is the energy. Coming from the previous one to a formula, E is equal to HF. Okay, means that here when you substitute inside this one, it becomes Ke max is equal to E minus V. What is phi here? Phi here we call it as a work function. Okay, work function of the metal. So the work function, so which represents the minimum energy, so with which an electron is bound in the metal. So means that here different metal have different work function. Okay, when you look at table 21, sorry, table 27.1, okay, so the highest one here is due to PT, okay, the value here is a 6.35. The work function is 6.35. So PT here is a platinum. Okay. So next part. So explanation of classical problems. Okay. So the first one here. So the effects is not observed below a certain cut-off frequency Fc. Okay, sometimes we call it as a cut-off frequency and sometimes we call it as a threshold frequency. So since the photon energy must be greater than or equal to the work function phi. Okay, so without this, electrons are not emitted regardless of the intensity of the light. Okay, number 2. The maximum kinetic energy depends only on the frequency and the work function, okay, not on the intensity. Okay, so the absorption of the single photon is responsible for the electron's kinetic energy. So number 3, the kinetic energy maximum increases with the increasing frequency. And the last one here, number 4. So the effect is instantaneous since there is a one-to-one interaction between the photon and the electron. Okay, so this one is a verification of the Einstein theory. Okay, so experimental observations of the linear relationship between kinetic energy and the frequency confirm the Einstein theory. Okay, so the x-intercept is the cutoff frequency, Fc, and then photons with a frequency less than cutoff frequency don't have sufficient energy to eject an electron from the metal. So it means that here, in this case, so what happened to your maximum kinetic energy? Become 0. Why kinetic energy maximum 0? So basically, this one coming from the formula Ke max is equal to E minus work function. So it means that here, when you don't have a frequency, of course, you don't have the energy. Okay, so when you don't have the energy, so what happened here? No electron ejected, and suddenly your maximum kinetic energy become 0. So here you have a graph of kinetic energy maximum versus frequency. Okay, so it means that here you have a linear graph here at this situation, Fc here. So this one is a cutoff frequency, and sometimes we call it as a threshold frequency. Okay, so it means that here if your value of frequency is higher with the higher value compared to the cutoff frequency, means that here you have a higher value here. So what happened here? Okay, so your kinetic energy maximum should be increasing. But if your frequency here, okay, is below cutoff frequency, means that at this situation, so what happened to your Ke max here? So Ke max here at this situation should be 0. Okay, means that here your Ke max here, okay, is less than Fc, automatically become 0 lah. Okay, cut off wavelength. So cutoff wavelength, okay, so the cutoff wavelength is related to the work function. Okay, so here lambda t is equal to hc divided by work function. Okay, so it means that here what happened when your frequency is equal to cutoff frequency, automatically your Ke max becomes 0. When your Ke max becomes 0, okay, so means that here from this formula, for example here, okay, so coming from this formula, okay, when your Ke max here becomes 0, why your Ke max here becomes 0? Because at cutoff frequency, okay, so means that here automatic your here your HF here is equal to work function when your Ke max is equal to 0. Okay, so you know that here HF is the energy. Okay, so what is the frequency here? So coming from the formula of frequency, C is equal to F lambda. Okay, so C is equal to F lambda. So means that here when you substitute F inside this one, so automatic F is equal to C divided by lambda. So here the formula, a new formula become C over lambda is equal to work function. Okay. And when you rearrange the formula, okay, automatic. So lambda C is equal to Hc divided by V. Okay. So means that here all of this one coming from the energy. Okay. Okay. So SI unit should be meter. So lambda C we call it as a cutoff wavelength. Okay, this one happen when you have when your frequency is equal to cutoff frequency. Okay, so the wavelength greater than lambda C incident on the material with a work function. Okay, we don't result in the emission of photoelectrons.
Okay, to be clear, due to cut-off wavelength, so you know that the formula of cut-off wavelength, lambda c is equal to hc divided by work function. Okay, then coming from the previous formula, Ke max is equal to hf minus v, where hf here is the energy. Okay, then when your frequency here is equal to cutoff frequency, so automatic your Ke max become 0. Okay, when your Ke max becomes 0, when you substitute inside this formula, so automatic this one become 0 is equal to HFC minus work function. And when you rearrange the formula, HFC is equal to work function. Okay, and then we go into the previous formula due to speed here, speed of light. So C is equal to FC lambda C. So this one coming from the formula of C is equal to F lambda. Okay, so when you rearrange the formula FC here is equal to C divided by lambda C. And then when you substitute FC inside this formula, so automatic it become HC over lambda C is equal to work function. And when you want to produce the lambda C, and then you rearrange the formula again, so lambda C here is equal to HC divided by work function.
Okay, so photocells. So photocells are an application of the photoelectric effect. Okay, so when light of sufficiently high frequency falls on the cell, a current is produced. For example, here you have a street light. Here you have, and then you have the garage door openers and also the elevators. Okay, so now we go into the example 27.1. Okay, a sodium surface is illuminated so with a light of wavelength 0.3 micrometer. Okay, so here you have the wavelength. Okay, the question given to you wavelength. So then you are given the work function for the sodium is 2.45 eV. Okay, so means that here this one should be your phi. So now we want to calculate the energy of the each photon in electron volts. Okay, so B, you want to calculate the maximum kinetic energy of the detected photoelectrons. And the last one, you want to calculate the cut-off wavelength for the sodium.
Okay, so based on example 27.1, so you are given the lambda here is 0.3 micrometer. So this one is equivalent to 0.3 times 10 to the power of negative 6 meter. Okay, and then the work function for sodium is, so the work function phi here is a 2.46 electron volt. So the first question here, you want to calculate the energy of each photon in electron volt. So it means that you want to calculate E in unit electron volt. Okay, so automatic. So the formula become E is equal to HF. Okay, so your question given you lambda, your question given you work function. Okay, so now we want to calculate energy. So how you calculate the energy? So by using this one, E is equal to HF. So then you can substitute here. This one, F here is equal to, okay, C is equal to F lambda. F is equal to C divided by lambda. So automatically it become H C over lambda. So where H here is equal to a Planck constant 6.63. Okay, 6.63 times 10 to the power of negative 34 joule second. Okay, and then your C here is the speed of light, 3 times 10 to the power of 8 meter per second, and then divide by your lambda here. So you are given the lambda 0.3 times 10 to the power of negative 6 meter. So you can calculate the value of energy here. Okay. So 6.63 times 10 to the power of negative 34. And then time 3 times 10 to the power of 8 divided by 0.3 micro. So automatically the value here should be 6.63 times 10 to the power of negative 19 joule. Now you want to convert joule to electron volt. Okay, remember again. So 6.63 times 10 to the power of negative 19 joule. Okay, so this one you want to convert to electron volt, means that you want to cancel joule. Okay, so how? So automatic, you know that 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joule. So means that here joule and joule you can cancel out. So automatic it become 1.6 times 10 to the power of negative 19. So it become 4.14 electron volt. So that one for question A. Okay, and next one we go into question B. Question B here. Okay, so the maximum kinetic energy of the ejected electron. Okay, you want to find Ke max. So Ke max, okay, is equal to E minus P. Okay, so then here E here already calculate here 4.14 EV, and then you are given the work function here is 2.46 EV. So here both are in the same unit. Okay, if this one if you not convert this one to EV, let's say you just take off all of this value, then you minus this value, automatically this one should be wrong. So it means that this one must be in the same unit. Okay, and final answer should be okay, so the answer should be 1.68 EV. Okay, so next one here, you want to calculate the cut-off wavelength for a sodium. Okay, you want to calculate the cut-off wavelength of the sodium. So automatically you can use the formula lambda C, the cut-off wavelength, is equal to, okay, so it's equal to H C divided by work function. Okay, so means that here the value of H here is 6.63 times 10 to the power of negative 34 joule second. Oh, sorry, so this one is a joule second. And then your C here is 3 times 10 to the power of 8 meter per second. And your work function due to sodium is 2.46 EV. Okay, remember this one in unit EV, but this one in unit joule. Okay, so it means that here this one you need to convert this one to the joule first. So it become, okay, it become 1 EV is equal to 1.6, okay, times 10 to the power of negative 19 joule. So EV and EV you can cancel out, second and second you can cancel out, and then joule and joule you can cancel out, and final answer, final unit become meter. Okay, so you can calculate here 6.63 times 10 to the power of negative 34, and then times 3, 10 to the power of 8 divided by 2.46 times 10 to the power of negative 19 times 10 to the power of 1.6. So final answer become, okay, so this one become 5.05 times 10 to the power of negative 7 meter. Okay, so done.